Good afternoon. Can you hear me? Okay, thank you for the response. What about the rest? Can you hear my voice? Good afternoon. Okay, let me share my screen. How is everyone going? Have you taken your vaccination? Or you are still waiting for the vaccine? Just wonder how many of you have taken it? No, you guys are still waiting. Oh, okay, waiting for second dose. Okay. So let's start our lectures today. Let me start recording first. Okay, so Long Yao Ting, what have we learned last week? You still remember? Long Yao Ting, compensate the semiconductor. Yes, you are right. So in the compensated semiconductor, we are going to have a ND and NA. So if ND is more than NA, which type of the semiconductor is this? Lao Rok Jing? Are you here, Lao Rok Jing? Okay, if ND is more than the NA, which type of semiconductor is this? Yeah, and type. If NA more than ND, Chua Yu Yang, are you here? Yep, P type. If NA is equal to the ND, what kind of the semiconductor is this? Chan Xu Pian, are you here? If ND is equal to the NA, what will it become for this compensated semiconductor? Yeah, intrinsic semiconductor. Thank you very much. So for the NA and D, we also learned about the formula. NO equals to the ND minus NA plus ND minus NA divided by 2 square plus NI square. So if this is an N-type, and then your PO will be equal to the NI square divided by the NO. Okay, same thing happened to the PO. If this is a p-type semiconductor, Na more than ND plus Na minus ND plus Ni squared. So this is a p-type. And then your NO will be equal to the Ni squared divided by PO. Also, we also learn about one thing. Okay. We also try to link the formula together, if you still remember. Last time we learned about this. NC exponential minus EC minus EF over KT. Okay. So if this is the, let's say, if this is an N-type semiconductor, we can rewrite something like this. Exponential minus EC minus EF over KT. Then we can try to rearrange everything. So it will become EC minus EF and KT ln NC over ND. Okay. So if your semiconductor containing ND and Na, which your ND is more than the Na, this thing should become ND minus Na. Okay, this is what we have learned so far. Same thing happen if we have this At ln Mv Na minus Nv. Okay, so this is what we have learned so far. And don't forget, next Monday will be our test during the lecture hour, 1 to 3 p.m. Our test. So the teaching content, the covering area will be until the content this week. Okay. So the question is quite simple. I believe you guys can do it, no problem. So good luck to all of you. So let's talk about the lectures today. Okay, lecture slide. So the slide is for the educational purpose only, and all the materials are obtained from this source. And you are welcome to go to see this book if you are interested. Okay, so we learn about all the electrons and the holes. So how do we make this thing move? So for example, last time when we are learning a thing in the semiconductor, if we didn't connect to anything, okay, we will say that this condition will be in the thermal equilibrium. If we didn't connect anything. But as we know, when we are talking about all the electricity, we are going to connect this to a power. Okay? So when we are connecting this semiconductor into the power, so force will be going here. You are providing the external energy to push the electron. So in the semiconductor, there are two types of movement. One is caused by the external energy. Okay? This external energy means that you are providing the electric field inside there. If you are providing the electric field inside there, it will force the electron to move from one side to another side. So this is the first type of the movement. Second type is based on the concentration. What is the concentration? So for example, if you have a semiconductor, for example, a PN junction, something like that, so maybe one side you will be full with the proton, another side will full with the electron. Okay, this one full with a hole. So this one electron, holes. So the second type of the movement is based on the concentration. So in this part, electron high concentration. Okay, then hole low concentration. By this part, hole is a high concentration, but electron low concentration. So in this case, the high concentration will flow into the low concentration, which is the electron. So electron in here, it will flow from the high concentration to the low concentration, just like the water flow, okay? From the high concentration way to the low concentration way. On the other way around, the hole will be flow from the high concentration to the low concentration. Okay, so we know that right now there are two types of the movement. The first type is based on the external energy. Okay, in this case, the movement of it we call it as a drift movement. Second type, we call it as a diffusion movement. So when we are talking about the drift movement and diffusion movement, both of them will have a different energy, different calculation, different formula to be applied. Okay, let me remove all this thing. So right now we got drift and diffusion. Whenever we talk about drift, we know that it's caused by the external force. And this is based on the concentration. When we talk about external force, then electric field is provided. So there's one thing you need to know. This is the electric field. We denote that as a E. But when we are talking about diffusion, diffusion is based on the high concentration to the low concentration, which means that in the semiconductor, if it has a distance of x, the concentration, for example, from high to low. When you change from high to low, the concentration will be changing according to the distance. So you have to know that the concentration will be equal to the, let's say if your concentration is D and O, then it should be dx. So this thing, we normally use this thing to play around with it. But first thing we need to know is the drift. Okay. If there is an electron moving or hole moving, there will be the current. Okay. Under the drift, we call it as a drift current density. We try to quantize this as in a density. Okay, density, I believe you guys already know how to calculate that density. And in this drift, we normally will ask to calculate the drift current density. How are we going to calculate the drift current density? So drift current density, we normally will write in terms of J. Then this J will be having a special formula for it. So this J is written in this way. E mu n plus mu p with the electric field. So let's see one by one. This E is a constant, 1.6 times 10 to the power negative 19. And this one is the electron concentration. P is the hole concentration. E is the electric field. But what are the mu n and mu p? Mu n and mu p, you can think in this way. You can think in this way. You can assume that this is the way we measure how it moves, how the electron or hole move. Okay, to be more specific, we will call this behavior, we call it as a mobility. Okay, so this is the first formula that we need to learn. This thing we will deal with later. So let's get back to here. Mobility, this two mobility basically is just a constant value. This constant value we can obtain from the table in the chapter 5. Okay, which is this. Let's turn it on again. Okay, you can see that in this formula, this table, the mobility is somewhere around here. This one. Silicon, when inside the silicon, the electron and the hole will be having the different mobility constant value. Same thing happened to the germanium and the gallium arsenide. Actually, everything are just a constant. And we just need to know how to apply it only. Okay, so in this case, get back to here. Yeah, I will write it nicer. J will be equals to E mu P plus mu N E. E constant 1.6 times 10 to the power negative 19. Mu N and mu P is the mobility. see the table. E is the electric field. Normally it's given in the task, in the question normally. Okay. Right now, what about P and N? To calculate P and N, you need to see what kind of the semiconductor is that. So if the semiconductor provides you the value of ND and NA, then you calculate your N using the NO formula, which is ND minus NA divided by 2 plus square root ND minus NA divided by 2 square plus NI square. This is a formula. So in this case, you also need to check that whether your ND and NA, which one is bigger. So if your ND is bigger than NA, then your PO, your P here, should be calculated using NI squared divided by the NO. On the other way around, if your NA is less than if your NA is more than the ND, then you have to use the other formula to calculate it, which is you need to calculate the PO, NA minus ND divided by 2 plus NA minus ND divided by 2 square plus NI square. Then your NO will be equal to NI square divided by PO. Okay, this is how we calculate it. So by using these two formula, you are going to obtain your N and P. Then your N and P, you just need to replace into these two variables. So in this way, you are going to calculate your answer back. So this is how we calculate the drift current density. Okay, back to this. E equals to mu PP plus mu N B. Okay, if we didn't consider this E, electric field, we just consider this thing. This thing, we will say this is the conductivity. To make it more layman term, this thing is see how effective it conducts electricity. Okay. If we have the conductivity, we will also be having the resistivity. So resistivity we normally denote it as this rho, which is equal to 1 over this. Okay, 1 over conductivity will become the resistivity. So in the future, this resistivity will be used to calculate the resistance of the semiconductor. When we are talking about the resistance, we will link it to V equals to IR. This resistance will be the one inside this resistance. Okay, so this is how we calculate the resistance. Basically, at first we need to know what is this P, this N, mobility, and the electric field. From here, we can keep on calculating until we calculate the resistance. Okay, let's get back to the slide. So, introduction, the net flow of the electron and the moles in the semiconductor will generate the currents. As I mentioned just now, whenever there's an electron or the hole moving, it will compute the current. The process when this charged particle move requires a transport. Okay? So, transport actually is a movement. The movement that I tell you. There are two types of the movement. The first type is a drift, second type is a diffusion. So the drift is the external electric field applied on the semiconductor. They will produce a force to make all the electron move. Okay, this is a drift. So when the electron and the hole are moving together, they will be from the net acceleration. Then the diffusion is the one that I tell you, from high concentration to low concentration. So let's go back to the drift carrier. Okay. First, we will be having the current density. This current density is the one that I tell you just now. This is the formula that we are going to use in this lecture. Okay, this one. Okay, N and the P is the concentration of the electron in the hole that we studied previously. So this table is the table that I showed just now. Okay, we normally use this table as our constant value. Okay. Let's see how we're going to apply this formula. If we have this question, consider the gallium arsenide. You get all these things? Consider the gallium arsenide with a doping of the Na equals to 0, Nd equals to 10 to the power 16 cm cubed. Assume to compare ionization and electron and mole mobility given the table just now. Calculate the brief current density when E equals to 10. So this one is a gallium arsenide. We need to know the mobility first before we proceed. Okay, gallium arsenide. Mn will be equals to the 500. Mu P will be equals to the 400. Okay, by having this information, we are going to calculate our answer right now. So the big formula is this: J equals to E mu N M plus mu P P multiplied by E. And then we know the Nd and Na. Okay, so NO will be equal to the Nd minus Na divided by 2 plus square root Nd minus Na divided by 2 plus Ni squared. Okay, in this case, we didn't get the Ni squared. We try to use the one in the table first, okay, to make everything simple. Ni squared intrinsic 1.8 times 10 to the power 6. Okay, so by putting all the value inside, this should be approximately 10 to the power 16. Okay, then your PO should be using this 1.8 times 10 to the power 6 divided by 10 to the power 16. So let's see this. What's the value? Okay, so this is equals to 3.24 times 10 to the power negative 4. Okay, after having this NO and PO, we are going to replace every single value inside there. 1.6 and 10 to the power negative 19. Okay, mu P, 500 multiplied by 10 to the power 16 plus 400 multiplied by 3.24 times 10 to the power negative 4 multiplied by the E, which is equal to 10. So let's see this. This will be equal to E mu N plus mu P multiplied by E. Okay, so eventually we are going to get the answer as stated in the here. It is about 136 136 A over Cm squared. Okay, you can see that here is Cm squared because in the semiconductor, it actually having the area over here. Okay, density, current over the area, it will become the density. So this is how we get the unit come from. Okay, A, we normally know that A is ampere. Area. Ampere over area, we get the density, current density. Okay, can you understand this, everyone? If you think you can understand that, yes. Okay, at this moment, you don't have to know how do you get the formula. We just think how to apply the formula only. Okay, cool. So let's try one more example here. So let's try this. So we were having the silicon, gallium arsenide, and germanium. So calculate the brief current density of all these three semiconductors. The table wise, I can copy the table to you. Table. this is a table. Okay, credit stream. Okay, have you calculated everything? Or you are still doing? How many of you are still doing? Can you please tell me? Okay. By the way, once you have done everything, let me know. Okay. Okay, how is everything going? Still doing or already complete? Blue jamming. Are you here? Chu Zhang Heng. Oh, okay. Complete everything first. Complete the gallium arsenide and the germanium also. Can you explain about the simplified equation of J-cube? Are you saying this? This formula is it? Which simplified equation are you talking about? Mr. So Yan Chang. It's 6. Okay. The reason you do this is because NA will be equal to 0 already. So he straight away assumed that the PO is a very, very small value. Okay? So that's why straight away using this formula. He assumed that this one will be 0. Okay? So that's why, because this one is a very, very small value, so he assumed that this is 0. Because it's considered value 4 already. Then he straight away using mu n multiplied by the ND. Because ND is always more or less equals to the N. Okay, let me write here. N is more or less equals to the ND. So he assumed that P very small. Ignore. But in the real world, normally when we are doing everything, you better calculate every single item. Okay. So Yan Chang, can you understand? Okay, have you done everything, everyone? So Yan Chang, have you done everything? Lu Juemin, Lao Lục Tinh, Chan Xu Pian, Tan Xin Shen. Okay, let's calculate. Give me one moment. Okay, so let's see. So in this case, we know that the ND is more than the NA, right? And we know that this is an N-type. If N-type, we need to calculate this ND minus NA divided by 2 plus square root ND minus NA divided by 2 plus NI squared. And then you calculate your P using the NI squared divided by the N. So we deal with the silicon first. So when this one is a silicon, what's the N and what's the P? So let's pick someone to answer me. Teo EC. What's the N and what's the P? Are you here, Teo EC? What is the N and what's the P for the silicon? Okay. And about 14. P is, what about P? 25000. For the rest of you, do you get the same answer? Chu Zhangheng, what's the answer for the N and P for the silicon? Okay. Lao Lộc Jing, what about you? Your N and P, do you get the same answer? Okay, good. Then we have the N and the P. So we can calculate the J. So back to DOEC just now. What's the drift? 6.804 A over cm squared. Chu Zhangheng and Lao Lộc Jing, do you get the same answer for this? Okay, cool. Okay, so this is for the silicon, very easy to be done. So let's go for the germanium. Where's the next one? Gallium arsenide first. Okay, let me pick some guy to answer. Then I get another guy to verify. Yong Qie. What's the answer for the N and P for the gallium arsenide? N and P. Okay, Yong Qie saying that the first one 9 to the power of 14, I believe should be the same because it's using the same formula, just that your P will be slightly different. Okay, let us get the verification. Wang Chongye and Han Xiang, do you get the same answer for the N and P? Okay, what about Wang Chongyi? Wang Chongyi, are you here, Wang Chongyi? Okay, seems he may be not here. So, Ng Wei Hong, do you get the same answer for N and P for the gallium arsenide? Okay, cool. So, what about your J? Your Jie? Your drift current density? What about J? 42.84 for AOCM squared. Han Xiang and Wei Hong, do you get the same answer? Okay, cool. So let's move to the next one. The next one should be a germanium. So I believe the n should be the same also, should be equal to 9 to the power of 14. But what about the p? Lim Wan Yang. Are you here, Lim Wan Yang? Yes, Mr. Lim Wan Yang, are you here? Okay, looks like Lim Wan Yang and Wong Chong Yi are not here. Hua Yihang, are you here, Hua Yihang? Okay, what's the answer for your P? Okay, 6.4 times 10 to the power of 11. Okay, let's get some verification. Lim Yong Chuan, Chua Yu Yang. Do you get the same answer for this N and P? Okay. What about your J, Hua Yihang? Excuse me. Okay, let's wait for Hua Yihang's answer for the drift current density. Yes, Mr. Hua. Can be 1.84 A over cm squared. So Lim Yong Chuan, Chua Yu Yang, you get the same answer for this? Okay, we get a slightly different answer now. 19.68, 19.66. Okay, Hua Yihang, I think you might want to double verify your answer. Okay. Wong Ka Seng also get 19.66. Okay, there might be some miscalculation. Okay, maybe let's try another example. Right now, I'm going to change this, let's say, 10 to the power of 20 and 10 to the power of 10. Okay, we calculate these three items and its drift current density. Okay, how do you do this? Lim Wan Yang and Wang Chongyi are still here. Why you not replying just now? Where have you been? Okay, all right. Okay, we try this again. What about Wang Chongyi? Already missing. Okay, where have you been just now? Okay. Okay, we try to do this again. Right now, I change the NA and the ND. Hi everyone. After doing this, we take a maybe short 5 minute break for a toilet break. We come back by maybe 2:15. Okay? Okay, everyone, shall we continue? Is everyone here? Can you hear me, everyone? Okay, let's continue here. So in this question, NA given, ND given, then E we maintain the same. So let me choose one guy to answer this question first. Hu Hengdong, what is your N and P for silicon? Hu Hengdong, are you here, Hu Hengdong? Okay, tell me your N, P, and also J, these three together. 2.25 CMS cube, is it? P, what about P? 10 to the power 20 CMS cube. What about J? 26800 A over CM squared. Okay, let's verify the answer. See who can check. Wong Ka Sing, do you get the same answer as Mr. Hu Hengdong? Okay, let's pick the second one. Yong Ming Liang, what about you? Do you get the same answer, Yong Ming Liang? Okay, good. So right now, Yong Ming Liang, tell me the guidance answer I want. These three. Yeah, Mr. Yong Ming Liang. All these three information, what do you get? Okay. 3.24 times 10 to the power negative 8, which is a pretty small value. P is 10 to the power 20. Then J is 22400 A over CM squared. Okay, let's check. Lim Wen Yang, do you get the same answer, Lim Wen Yang? Okay. Wang Chongyi, what about you, Wang Chongyi? Do you get the same answer for this three item? Okay. So let's see the third one. Lisa Lim, what about you? You get this three answer for the gallium arsenide. Lisa Lim, are you here, Lisa Lim? This three is for what? Gallium arsenide or germanium? Lisa Lim, I'm saying these three items. Do you get the same? Yes means the same or? Okay. So Lisa Lim give us the answer for the germanium, I believe. N equals to 5760000. Then P equals to 10 to the power of 19. Then J equals to 1064000. Okay, let's check. Okay. Chia Chai Xiu, you get the same answer for the germanium side. Okay. Tan Xin, are you here, Tan Xin? What about you? Do you get the same answer for this three item? Okay, good. So basically, this thing very simple only. All you need to do is to put in the answer, then calculate all the things. That's it only. Very simple and easy. So let's continue to our lecture. So typical random behavior, okay, for the electron or the hole, it will move without any specific pattern. But if you are trying to apply the electric field here, you can see that this thing is shift a bit, okay? Because electric field shift him when it's moving. Even though you randomize moving, but all will be shift together. So there will be a net drift of a hole in the direction of the E, okay, which is this direction. Okay, so this one is a mobility effect, nothing much. Okay, but what caused the mobility effect? So there are two phenomena that cause the mobility effect. One thing is the phonon or the lattice scattering. Another one is the ionized impurity scattering. EID. What are these two things about? So do you remember that last time when we are learning about cubic, okay? Cubic or this thing. So one atom will be on the corner there. So supposedly, if you didn't add any impurities inside, so your atom will be static on here. It never move. But when you're trying to provide the energy inside this atom, inside there, all the electrons are start vibrating, but they are still maintaining in this location. Okay, the vibration caused there, it will affect the mobility. But the atom still there, it never changed. It's still there, but it will vibrate on itself. Keep on vibrating at the same location there. The vibration, it will affect the mobility. This kind of the phenomena, we call it as a phonon or lattice scattering. Why do we call it this? Because last time, we learned about the lattice here, A and A here. This is a lattice. The other one is the ionized impurity scattering. Ionized means if this is the atom, if you accidentally add something impurities inside, the external electron will hit inside the electron of the original semiconductor. While there are some collision between all the electron, it will cause the changes of the mobility. Okay, this phenomenon we call it as a ionized impurity scattering. Okay, and these two are having one formula for the changes also. So your mu L, lattice scattering mobility, will be corresponding to the T to the power of 3/2 because it only affected by the temperature only. Okay, but another one for the ionized one, ionized mobility, it will be affected by the 3/2 and also the concentration given over there. But this is for your knowledge only, you don't have to worry about it. It's a graph, nothing much. Okay, but imagine if you are having these two mobility, mu I plus mu L, you need to find the total mobility. Okay, in order for you to calculate all these, for example, this one the mu PP, all these are calculated from here. So sometimes you are given this a field mobility, then you were asked to calculate the total mobility. This thing, it looks something like a resistance. Okay, you see that when we are going to calculate the resistivity, we also use the same formula. But when we are calculating the total mobility, we are also using the same formula. Okay, so this one is a conductivity. Conductivity, I told you just now. Okay, e to the power mu nm plus mu pp. This will be your conductivity. But when you are calculating your resistivity, this will be equal to 1 over conductivity. That's it only, very simple. So this is a graph, nothing much. The important thing one is this. Okay, right now, we all know that This will be equal to the current over ampere. Okay, current density. This will be the ampere over cm squared. Then we also have another formula. Electric field will be the voltage over the length. L is the length of the resistor, of the semiconductor. So when you're using V divided by L, you can calculate the electric field. Okay, so back to this. J is equals to the conductivity multiplied by the E, right? Just now we playing around with this. This is E mu n n plus mu p p multiplied by E. But if we are knowing these two features, this and this, we can replace the value inside. I over A equals to the mu V over L. Okay? And then we are going to rearrange everything. We put the L in here, we drag the conductivity in here. L A I equals to V. Then this thing will be equals to the V equals to the IR, where your R will be equals to the L over conductivity multiplied by the A. And you also can further write it as the resistivity, rho over A, because your conductivity is 1 over rho. Okay, so basically the Ohm's law is coming from here. How are you going to generate the resistance? It's based on the length of the semiconductor, the length, and the area here, and then also the conductivity, where we can calculate using the formula that we learned just now. Okay, at this point, can you understand? Okay, let's try this example. Like this, let me remove all this thing. Let's write down everything first. At first, your ND will be equals to 5 times 10 to the power 15 cms cubed. And then the resistor is R, resistance 10k ohm. And then your current density J equals to 50. Your E will be equal to 100. So he asks you to calculate this one, conductivity. But how are we going to calculate this? So let's see. Okay, we got this formula here. V equals to rho L over A I. Okay. And then the L is not given. Then the E is given. And E is given. Then we can write something like this. Okay, we refer back to the very first original formula. Okay. We know that okay, we have this information only. 1000 equals to rho L over A. L and A, we don't know that. Then we got a J, we got a E, 50 multiplied by the conductivity, and then multiplied by the E. Okay? So basically from this thing, you can start doing it. You can calculate the conductivity. That's it only. 50, 10 divided by 100. You know that your conductivity will be equal to the 0.2. Okay, very simple. So let's see if you are given some of the information further. Okay, this thing is very simple. He asks you to calculate the current density. Then when the V is applied, then E also applied. V is given you by 5. Okay. So let's see. You are given R. Again, we organize everything again. So the conductivity, we can calculate it. Let's see if we can calculate more information from here. 0. This one is 51, 100. So this one is a 1, 2, 0.2. Then your J is 50. Your E is 100. And then your V is equals to 5. Also, we have this formula. Okay. So right now, we are having the 5. Then we also know the R. R is the resistance. Then we can calculate the A, which is the I, V over R. And then we know this V, we know this I, we know this rho. Then we can calculate the relationship between the L and A. Okay? Very simple only. So maybe we try one more example. Let's say, okay lah, maybe we'll try next time. Okay? Today we end the class earlier, shall we? Yeah, 0.5, sorry. Write something on this one. This one 0.5, not 0.2. 0.5. My bad. Okay. Today we end the class earlier. Okay? Everyone? Is everyone okay with this arrangement? Okay, I think that's all for today. Thank you very much. Have a nice day. So for those who are selected for the EAC interview, please join the briefing later.